Now, I will show you something else, which is quite interesting, and that is how the behavior of the period is on the mass of the object. I have here another car, which weighs roughly the same. I'm going to add the two together, and so we get N2 is about 372 plus or minus 1 gram. The plus or minus 1 comes in because our scale is no more accurate than 1 gram. So we put them both on the scale, and we find this to be the uncertainty. So now, I'm going to measure the 10 periods of this object with mass m2, so twice the mass. So that should be the square root of m2 divided by m1 times 10 times the period of m1. And so I can make a prediction, because this is the square root of 2, and I know what this is. So I will take my calculator, and I will take the square root of 2, and I multiply that by, let's take 15.15. And so that comes out to be 21.42. 21.42. It's not clear that this 2 is meaningful. And now comes the $64 question. What is the uncertainty? This is a prediction. And this now becomes a little tricky. So what I'm telling you now may confuse you a bit. It's not meant to be, but I really won't hold you responsible for it. You may now think that the uncertainty in this measurement follows from the uncertainty in this, which is true, which is about 0.6%, and from the uncertainty in this. So this has about an uncertainty of 0.6%. I got it low because I measured 10 oscillations, you see. The uncertainty is only 1 out of 150, which is low. You may think that the uncertainty in there equals the square root of 372 plus or minus 1 divided by 186 plus or minus 1. And now you may argue, and it's completely reasonable that you would argue that way, you would say, well, this is roughly 0.25% error here under the square root, and this is roughly 0.5% error. 1 out of 200 is about half. So you would add up the two errors, 1/4 plus half, that's about 0.7, and because of the square root, that becomes 0.35%, and that's wrong. And the reason why that is completely wrong, that has to do with the fact that these two errors are coupled to each other. See, the 186 is included in the 372. The best way I can show you this, suppose I measured m1 divided by m1, which would be 186 plus or minus 1 divided by 186 plus or minus 1. That number is 1 with 100 zeros. This number is 1. You have the mass of one object, you divide it by the same object. Whereas if you would say, this is a 0.5% error, and this is a 0.5% error, you would say the ratio has an error of 1%, and that's not the case. So I will not bother you with that. I will not hold you responsible for that. But it turns out that if you do it correctly, and you take the error of this into account of about 0.6%, that the error in this ratio is really much less than 0.2%. You can almost forget about it. I will allow generously for a 1% error in the final answer. And so I stick to my prediction that the 10T of double the mass is going to be like this. And now we're going to get the observation. 10T times m2, which is double the mass. And that, of course, always has my uncertainty of my reaction time. There's nothing I can do about that. And we will compare these two numbers. So I will put the other mass on top of it. Comes here. Tape them together so that they won't fall off. There we go. So, I hope I did that correctly. The square root of 2 times 15.15. We'll give it a amplitude something like 30, maybe 35 centimeters. There we go. 1, 2, it's much slower, you see that. 3, 4, 5, 6, 7, 8, 9, I'm not looking, 10, 21.36. 21.36. You can round it off to 4 if you want to, and you see that the agreement is spectacular. Within the uncertainty of my measurements, comes out amazingly well. You could have removed this 2, of course, because if you have an uncertainty of 0.2 here, it's a little silly to have this little 2 hanging there. But you see that indeed this spring is very close to an ideal spring. It obeys Hooke's law, and it is also nearly massless.